Hello, and this is our presentation 2. I'm in a team with Alana and Cisco. An integral can be used to find displacement, such as area and volume under the curve. A definite integral has lower and upper limits in which it is bound by for a continuous function. In order to evaluate an integral, the function must be continuous on a closed interval a and b. These are only for definite integrals. To evaluate an integral, we just find the antiderivative of the function and subtract it by its upper and lower bounds. Simulation data points yield an approximate ratio that would give the approximate area under the curve. Using Monte Carlo, it generates a random set of points over and under the curve, and then it takes a ratio. A simulation of data points can be used on functions where taking an integral might be not as feasible, or it might be a more complex problem.
Expected value is the predicted value of a random variable where each value is multiplied by the probability of its occurrence and then summed up. This shows that in the long run, the average for the same experiment should approximately converge to the same value. What is meant by Monte Carlo in an integral estimation? Well, Monte Carlo is just one of the methods for solving integration by generating random numbers. It can be useful when solving complex problems and used for higher dimensional integration as well.
There's a statement that says we can estimate the value of any integrand no matter how complex the integrand. So why is this important? It's important because it's showing us that no matter how complex the integral is, we can approximate some sort of solution to obtain it. The Monte Carlo method can be used to figure out an integral or the area under the curve by using the underlying probability distribution of the specified concept. The Monte Carlo method can also be used for simulating the particles moving in nature, and we know this to be a random movement throughout nature. An example of this would be some type of machine shooting balls at a wall. You don't know where the ball is going to land each time on that wall or where it's going to hit. So that would be showing the randomization of that as well. So how can Monte Carlo be used to solve more complex distribution functions, and how can that function relate to the mathematics behind the determination of the yield of fissionable and fusionable materials? So Monte Carlo plots random points to determine the ratio or proportion of acceptance versus rejection to further find the equation of a curve. You would need to use this method if you don't know the equation for a given curve or for that given concept. It's to find the area under the curve. So the points that are under that curve would be accepted and the ones outside of it would be rejected. So the acceptance and rejection method for generating random variates is a way to solve more complex distribution functions, and that also can relate to a laser-generated particle beam simulation. Through that simulation, you would have a laser beam, and you don't know exactly where it's going to end up. So it's a randomization of where the laser beam is going to end.
Here we are evaluating the function e to the negative 1/3 x squared plus y squared cosine xy plus sine y. We are using the integral form from negative infinity to infinity. We first factor out a standard double normal distribution and then multiply by its expectation. We then plug in the equation we found earlier into MATLAB and compared it to its closed form. This demo shows the closed form using the original function and then the Monte Carlo simulation by factoring out a distribution. We see that the results it yields are very close and all fall within the upper and lower bounds.
Thank you for watching our video.